Hi there, welcome to this video. Thanks so much for clicking on and watching. Going to go through some mechanics questions to help prepare for the Edexcel A-level maths exam. It's paper 3, it's the applied paper, and it is next Tuesday, the 20th of June. So let's get started. Just to let you know that if you go to the show more button, which is just under the video, and drop down into the description, there are timestamps within the description. So if you wanted to just look at a particular question, one aspect of the course, you could just use the timestamps there. This first question is on projectiles. So whenever we have an object being projected, we get a symmetrical curve like this. It's being projected at a speed of u and an angle of theta. Now, what's going to happen is gravity is going to mean that it will slow down and reach a max, and then it will come back down, and that curve's meant to be symmetric. So whenever we have angles in mechanics, we've got the size of it, which is u, and we can resolve in the two directions. So opposite the angle is going to be the size of it, sine theta, and then adjacent to the angle is going to be u cos theta. And that's what we've got going on over here in this question. And what we've got to remember, that's the key thing in projectiles, is that that speed horizontally remains constant. If you walked underneath the object being projected, you could just walk at a continuous pace with that object up ahead of you, and you could get back to the ground at the same time. So you wouldn't have to speed up along the ground as it was being projected. The speed horizontally remains constant. Okay, so this question here, we've got t equals 0, projected horizontally along from the ground with a speed of u, angle of theta, moves freely under gravity and passes through point A when t is 4. So when t is equal to 4, we're here at A. As it passes through A, the particle is moving upwards with an angle of 20 and a speed of 15. So we can resolve again because we've got another angle horizontally and vertically, and this is going to be now 15. The size of that speed opposite the angle will be sine 20 and 15 cos 20. Now at the beginning we've got a bigger angle, but remember we've got u cos theta and u sine theta. But remember what we just said about the speed horizontally, that's going to be constant. So straight away we can write u cos theta is equal to 15 cos 20. So the speed horizontally remains constant. Now what we can do is use the fact that 4 seconds along, we've now got a different speed vertically, but we can use v is equal to u plus a t. So v being the speed after we've travelled for 4 seconds, that is going to be 15 sine 20 is equal to u sine theta, and then we're going to take acceleration due to gravity to be g, going in the upwards direction, but it's being slowed down, so we're going to write minus 4g because t is 4, and that's what's going to be slowing it down. So what we can do, the 4g is something we could put in our calculator, so let's take that to the other side. 15 sine 20 plus 4g is equal to u sine theta. And then because we've got an expression for u cos theta and u sine theta, if we just put u sine theta over u cos theta, we're going to get tan theta because those u's will cancel out. What is u sine theta? That is 15 sine 20 plus 4g, and just divide that by 15 cos 20. And then if you just do inverse tan of that, out will come the theta, which is 72.4 degrees. Now all we need to do is put that theta back in here and say that u cos of 72.4 is equal to 15 cos 20. So u is going to be 15 cos 20 over cos 72.4, and then that on your calculator brings out an answer of u being 46.5, and that's the speed, so it's going to be meters per second. This is part B of our projectile question. So we found out in part A that theta was 72.4 degrees and u was 46.5 meters per second. And now we're being told that there's a point B on the path where the particle is moving downwards at 20 degrees with a speed of 15. Now that matches that B will be over here as far away from that max as A is to it, and it's on its way down. So it's going to be symmetric, and it's going to go, this is going to be 15 meters per second, and the angle this time is going to be 20 degrees down. And like we did over here, we resolved horizontally and vertically. Vertically, this was 15 sine 20 because it's opposite the angle. Here, this vertically down is going to be minus 15 sine 20 degrees. And what we can do, because we're being asked to find the time taken for the particle to move from A to B, is you could find the time it takes for the max to be reached, and at that max V vertically is 0. So you could find how long it takes from the beginning to there. You could take 4 off, and that would give you the time to get to its max, and then you could double it because of the symmetry. But we could use V equals U plus AT, and U could be our initial speed just starting at A. Our V could be our speed by the time we've got to B, and our A is going to be minus G, and we could just solve for T. So let's do that. Then the final speed is going to be minus 15 sine 20. Initial speed is going to be taken starting from A because we're just asked for the time in between those points. So that will be 15 sine 20, and then we've got minus GT. So GT is going to equal 15 sine 20 and then plus another 15 sine 20. So if we double up the 15 sine 20 and divide by G, 9.8, you're going to get that T is equal to 1.05 seconds. So whatever way you do it, that is going to be your answer. Now, part C, the particle reaches the ground at point C. Find the distance. So here we're going to use, just going horizontally, that speed is distance over time. We're wanting distance. Distance is speed times time. So we need to find how long it takes. So we've just found the time to get from here to here. Remember what we said at the beginning, that horizontally it goes at a constant pace. The time to get from A to B, if we're just going along the ground horizontally, that's 1.05 seconds. The time to get to A was 4 seconds, and then the time to get from B to C is going to be 4 seconds. So the total time is equal to 4 plus 1.05 plus another 4, so that's going to be 9.05. And remember, the speed horizontally, the speed was constant. The speed is equal to our 46.5 cos of the 72.4. So all we need to do is to find the distance is times those two together. 46.5 cos 72.4 times 9.05 will give us a distance of 127 meters. This next question is a ladder question where we're going to be taking moments about A. We're going to be resolving forces horizontally and vertically, perpendicular and parallel to the slope. So we've got a ladder of length 5, mass 18, one end resting on a rough ground. So the ladder would potentially slip this way. So our friction needs to oppose that motion because we're told it's rough ground, and we're going to have mu r acting that way. The other end is end is at B, resting on a smooth vertical wall. So because it's smooth, there's no friction, but we will have horizontally a reaction from the wall. The ladder lies in a vertical plane, and we've got an angle where tan alpha is 4/3. So as soon as I see that, I would draw myself a triangle. I would put alpha, and the tan of it is 4/3. So the hypotenuse is going to be 5. Sine alpha will be 4/5, and cos alpha will be 3/5. Coefficient of friction is going to be mu, and that's what we're trying to find. We've got a woman of 60 kilograms standing on the ladder at the point C. So her weight acting down is going to be 60g. And the ladder is at the point of slipping, so this means that we're in equilibrium. So the forces horizontally, vertically are going to resolve and equal out, be in equilibrium. The ladder is modelled as uniform rod and the woman as a particle. Now, because we're told the ladder is uniform, that means we're going to have the weight of the ladder acting down here vertically, and its mass is 18, so that's going to be 18g. So all we need to do, the extra force is going to be here. There's a reaction force at the ground. So what you do first is we have to take moments about A. So when we're taking moments, it's just the forces that are acting away from A that are going to have an effect on the turning. The forces at A, which are the reaction at the ground and mu r, aren't going to have an effect on the turning. But the forces that are not at A, the only part that's going to affect the turn is the part that is perpendicular to the ladder. So the 18g, the 60g and the rw, we need to resolve them parallel and perpendicular to the ladder. So the 18g, here's going to be my alpha, and this acting down here is going to be 18g cos alpha. And doing the same at C, again this is alpha, and we're going to have 60g cos alpha. And then at the reaction at the wall, we can go perpendicular this way and parallel to the slope this way. Now looking at alpha, which is down on the ground, we can make an alternate angle here, and then because this is 90 degrees, this angle here will be the complement with alpha to make 90. We've got a 90 degree here, and this is actually alpha here. So we want the force that is perpendicular, so this is going to be RW sine alpha because it's opposite to that alpha. So it's a bit small on the diagram there. So let's take moments, and when we calculate moments, it's the distance away from where we're taking the moments times the size of the force. So the weight of the ladder is halfway along, so that's going to be 2.5 away from A times the size of the force, so that's going to be 18g cos alpha, because we're just taking the part that's perpendicular to the ladder, and then plus the lady is at 3 times 60g cos alpha, and because we're in equilibrium, that's going to equate to the RW sine alpha. Now cos alpha we know, and sine alpha, so we're just going to use these values, and we're going to get the RW. If we can just divide all of that by sine alpha, RW comes out to be on our calculator, because all of that we can just feed into our calculator, is going to be 135 g over 4. So just remember, when you put in cos alpha and sine alpha in, you're going to use these values, 4/5 or 0.8 and 0.6. So now we've found our W, we can then use the fact that it's in equilibrium, so forces up is going to equal forces down. So forget about all the parallel and perpendicular, just put your eyes on forces up, forces down. So which are the forces that are going up? We've got RG, and that must equal 18g plus 60g. So that's equal to 78g. And then horizontally, what forces have we got? We've got mu r is equal to rw, because they're going in opposite directions. So rw we just found out here, and the mu r is rg, so that's going to be mu times 78g, because this is rg, is equal to the 135g over 4. So all we need to do to find mu is do the 135g over 4, divide that by 78g, and if we do that, mu comes out to be 0.43. This next question is another moments question. So we've got Alice who weighs 50 and Bob who weighs 80 on a seesaw. Bob is X meters away from the end on one side. We've got a pivot exactly in the center. The seesaw is 4 meters long, and Alice is standing right on the other end. So for part A, draw on the diagram the forces on the seesaw due to just the two people. So Alice is going to have her 50g acting down, and then Bob will have 80g there. So that's all we're asked to do for part A. Part B, write down the total clockwise moment when we take moments about the center. So we calculate moments by looking at the distance away from where you're taking moments and then the size of the force. So we can see that Alice is going to have a clockwise moment because she's going to be acting down to keep that seesaw horizontal, but Bob is counteracting that, and his moment is going to go that way. So because we're asked to do the clockwise moment, if I do the distance Alice is, and if she's right on the end, it's going to be 2 times 50g, but then the Bob is going to be going anti-clockwise, so we need to take that away, and his distance, if he's X away from the center and up to the pivot is 2 meters, then this distance here is 2 minus X, so it's going to be 80g times 2 minus X. So we need to take that anti-clockwise moment away to get the resultant clockwise moment in terms of X. So multiplying that out, we're going to have 100g minus 160g and then plus 80gx. So 100g minus 160 is going to be minus 60g plus 80gx, and then if we just take 20g out as a common factor, I put the positive one first, that will be 4x minus 3. So that is part B. Part C, find the value of x for which the seesaw is in equilibrium. Because we've just done the take away and taken those moments about the pivot, if it's to be in equilibrium, then the resultant moment here will have to equal 0. So 20g 4x minus 3 will have to equal 0, and that's only going to happen because we've already factorized when 4x minus 3 is equal to 0. So 4x will equal 3, x will equal 3/4, and that will be there. X will be 0.75 meters, and then the seesaw is in equilibrium. For part D, given that Bob remains on the opposite side to Alice, describe with inequalities the range of x which the seesaw will tilt towards Alice. Now it's going to tilt towards Alice if Bob moves forward towards the pivot, and we're restricted because he's got to be on the other side. So if x gets bigger than the 0.75 but doesn't get any bigger than 2, it's going to tilt towards Alice because the moment going anti-clockwise will be reduced because that distance will be reduced. So the inequality is that Bob will have to be between 0.75 and 2 meters away from the end. So that's how we're going to write the inequality in terms of x. For part E, describe one limitation of the model. Well, one limitation is that Alice could not be standing exactly on the end. The seesaw might bend, it might not be just rigid, or the pivot might not act directly at a single point. So they would be the limitations of the model. So any of those for the 1 mark at the end of the question for part E. This next question is about variable acceleration. We've got a mass of 0.5 moving under a single force of F, and at time t we're given the velocity equation. Now we can see we're going to be using acceleration because we've got a mass and a force, so that's a hint that we're going to be using F equals ma. We've got the velocity equation, which is in terms of t, because we can see we've got these squared terms. When we differentiate v, because acceleration is the rate at which the speed changes with respect to time, so when we differentiate these two components, it's still going to involve t, and as this particle moves and the time goes on, then the acceleration is going to vary because it is in terms of t. So let's differentiate, because in part 1 we're asked to find the magnitude of the force when t is equal to 3, so we're going to be using this equation here, and that means we need to find acceleration. So differentiating each of the components, you're going to get 4 minus 6t in the I direction, plus in the j direction 2t minus 8. Okay, so we need to find what the acceleration is when t equals 3. So A is going to be 4 minus 6 lots of 3, which is 4 minus 18 minus 14 in the I direction, and then 2 times 3, 6. 6 minus 8 is minus 2 in the j direction. So what we can do is find the magnitude of that acceleration, because then we're going to be timesing it by 0.5 the mass. So we need to use Pythagoras. 14 squared is going to be 196 plus 2 squared, which is 4, and take the square root. So that's going to be the square root of 200. 200 is 100 times 2, and the 100 out the root is going to be 10 root 2. So the force using F equals ma is going to be 0.5 times 10 root 2, which is 5 root 2 newtons, or if you want to do that as a decimal, it is 7.07. That's part 1. Part 2, find the acceleration at the instant when it's moving in the direction of minus I minus j. So that's going to be in this direction. Now, even though we've gone minus I and minus j, the I and j components have to be the same. It doesn't matter that we've gone backwards and down, I and j components have got to be the same. Now, when something is moving, you're looking at the velocity equation, because remember, velocity is the vector for speed, and it gives us the speed and the direction, and we're told here it's moving in the direction. So we're going to use the velocity equation, and what needs to happen is the I and j component need to be the same to be moving in that direction. So all we need to do is say that 4t minus 3t squared must equal t squared minus 8t minus 40. Collect everything to one side. 0 is equal to 4t squared minus 12t minus 40. Take 4 out. T squared minus 3t minus 10 equal to 0. That's only going to happen if we factorize that bracket. It'll be t and t. We need a 5 and a 2. We need to be minus 5 and plus 2. So that's going to tell us t equals 5 or t equals minus 2. We can't have time being negative, so t is equal to 5. And what we need to do is put 5 back into our acceleration equation. So when t is equal to 5, a is equal to 4 minus 30, which will be minus 26 in the I direction, and 10 minus 2 plus 2 in the j direction, and then give it some units. That will be meters per second squared. This is part B of our variable acceleration question. Our particle P has mass 0.5, single force F is acting on it, and we've got the velocity equation that we've just been working with. But then for part B, we're told that P is at point A when t is equal to 1, and when t is equal to 2, it is at point B. And we're being asked to find, in terms of I and j, the vector that's going to get us from A to B. So this is all about the position that P is at, and in order to find position, we now need to integrate. So the position vector usually uses the letter r, so that's going to be the integral of v dt. So if you think about your speed time graph, you find the area under the curve, and that is the distance, and that is what we're finding here. We need to integrate. So integrating each component, you're going to get 4t squared over 2 minus 3t cubed over 3 in the I, and then in the j you're going to get t cubed over 3 minus 8t squared over 2 minus 40t in the j. Now let's tidy those up. 4 divided by 2, 2t squared minus t cubed in the I. In the j we've got t cubed over 3 minus 4t squared minus 40t. Now what we need to do is find where it is at each of those times. So at A, t is equal to 1. So A is the position. So just put t is equal to 1 into that equation that we've got for position. So that's going to be 2 minus 1, it's I. And then when we put 1 into the j component, we're going to get minus 131 over 3 in the j. So at B, t is equal to 2. So doing the same for B. If we put t is equal to 2 in the I direction, we're going to get 2 squared 4 times 2, 8, and then minus 8. So we're not going to get anything in the I direction. In the j direction, if you put 2 into that equation, you're going to get minus 280 over 3 in the j direction. And now to get from A to B, when you look at a common origin, if A is there and B is there, we need to go back down A and along B. So A to B is always the reverse vector, B minus A. So we just need to do minus 280 over 3j minus I minus 131 over 3j. So that's going to be minus I and then minus 280 over 3, and then this would be plus 131 over 3. That comes to minus 149 over 3 in the j direction. This is another vectors equation, and again we're given velocity in terms of t. Now we can see if we differentiated, acceleration would be constant for this question, but we're not asked to do anything with acceleration. For part A, we're just asked to find the speed. The speed is the magnitude of the velocity, so we need to take the magnitude. But first of all, we put in that t is equal to 0 and find what v is. So that's just going to be I, and then in the j it's going to be minus 3 in the j, and then the speed is just going to be the magnitude of v at that point. So that's going to be 1 squared plus 3 squared and square root, so that's going to be the square root of 10, and that will be meters per second. In part B, find the bearing on which P is moving when t is equal to 2. So we're moving again, so we're using the velocity equation. So when t is equal to 2, feed that into the velocity equation, you're going to get 1 minus 4, it's going to be minus 3 in the I direction. When t is equal to 2, you've got 6 minus 3, so that would be plus 3 in the j direction. So we're going to be going minus 3 plus 3, so we're moving in that direction. Now when we're trying to find bearings, you need to put in your north line, and the bearing is the angle you make when you turn clockwise from north. So if we find this angle here by using trigonometry, we've got a right angle triangle, so we need to do inverse tan of opposite over adjacent. 3 over 3. Inverse tan of 1 is going to be 45 degrees. If we do 270 plus 45 degrees, the bearing is going to be 315 degrees. Part C, find the value of t when P is moving parallel to the I. When we're parallel to the J, when we're parallel to the J, I is equal to 0. So we just make this component equal to 0. So 1 minus 2t is equal to 0. 1 is equal to 2t. So t is equal to half. So after half a second, we're parallel to J. For part 2, parallel to minus I minus 3J. So looking at these two components, if we times the I component by 3, then they will be worth the same. So for part 2, just do it here, 3 times the I component, 1 minus 2t. If we equate that to the J component, that will be 3 minus 6t is equal to 3t minus 3. So 9t is equal to 6. 6 over 9 is equal to t. T is equal to 2/3. This last question is a connected particles. We've got A, B and C with these masses, 3m, 2m and 2m. C and B are attached to each other, so they can be treated as one particle. They are connected by a light inextensible string. So light means there's no mass in the string, doesn't need to have to be taken into account. Inextensible, so the same acceleration throughout. We've got a smooth, light, fixed pulley. So again, no mass of the pulley, and smooth, so there's no friction at the pulley. System is held at rest and the strings are vertical. System released and A moves upwards. So part A show that the acceleration of A is g over 7. So first thing, we need to put the forces in. So we've got 3mg acting down, and here we've got 4mg. Now A is moving upwards, so I represent my acceleration with a double arrow, and what's going to drive it upwards is the tension in the string, and that same tension is going to be holding B and C back. So what we need to do once it starts moving is apply F equals ma. So we do that for both of the sides of the pulley. So at A, now I always apply F equals ma and look at the way it is moving. It is moving upwards. So what is moving it upwards? It's the tension. So the driving force is going to be stronger than the force holding it back, which is the 3mg. So that needs to be taken off, and that's the resultant force. So F is equal to ma. So that's 3ma. Then at B, what's driving it? Well, it's the weight of it going down. So 4mg is going to be larger than the tension, which is pulling it back, and that's equal to 4ma. So you always set your equations of motion up for either side of the pulley, and then because it's the same tension throughout, one tension will be positive, the one at A, and we've got minus. So we've got two simultaneous equations. Whatever's the same, you look at the sign. The signs are different, so we're going to add those two equations together. So if we add them together, you're going to get mg on the left is equal to 7ma, and then all we need to do is cancel the m's and get that g over 7 is equal to a. So in part 2, find the tension in the strings. So what we need to do here is just feed the acceleration that we've just found into one of the equations. Going to go in the first one because that's going to give me tension as positive. So the tension will equal 3ma plus 3mg. So that is 3ma plus g. 3ma we've just found is g over 7 plus a whole g, so that's going to be 8/7 of g. 8/7 times 3, it's 24 mg over 7. If you do 24 over 7 times 9.8, that is going to be 33.6 m, and that will be in newtons. Now having a look at part B in this question, because we're given some further information that when A has been moving 0.7 meters, C separates from B and falls away. So we're going to lose C, and because the mass on the B side is now less, this whole system is going to change. Because there's more mass on the A side, then the whole system is going to fall this way. It's going to go in the opposite direction. But because A is already moving, it's going to slow down and continue to move up before it then starts to move back down. So the system's going to change. So we're going to need to work out some new equations of motion. But first of all, in part B, we're asked to find the speed of A at the instant when this happens. So when this just happens, we can use the old information to find the speed that A is going to be 0.7 meters above its original position. So let's write our SUVATs. So S has been traveling 0.7. The system started from rest, so that's 0. We're trying to find the speed when it's been traveling 0.7 at the instant that C falls away. The acceleration is the acceleration we've already been working with, so that's G over 7. T is not involved, so I just leave whatever variable is not involved blank, and then I'm looking for an equation that doesn't involve T, so that's going to be V squared is equal to U squared plus 2AS. So V squared, which is what we're trying to find, is 0 plus 2 times G over 7 times 0.7. So that comes to 1.96. So V is the square root of that, which is 1.4 meters per second. In part C, find the acceleration of A at the instant that this happens. So we're going to have some new equations of motion to see what's going on. So we've got 3 mg acting down here and now just only 2 mg. So we're still going to have the tension, but that's going to change because there's less mass on the B side. So what's going to happen now, because the 3m is heavier, the system is going to go this way. So the equations of motion are going to change the other way around. So at A, we're going to get 3mg minus T is equal to 3ma, and at B, the driving force that's going to move it up is going to be the T minus 2mg is now equal to 2ma. Now again, we need to add them up. So we're going to get mg is equal to 5ma. Cancelling the m's, g over 5 is equal to the new acceleration. Now part D, I'm going to do that. D, find the greatest height reached by A above its original position. So if we do our SUVATs, so we're now looking for how far that's going to travel. We can have the initial speed is going to be our 1.4, which is the final speed when C is just separated, but that's the start of the new situation, so that's going to be 1.4. At the time when it's going to reach its greatest height, the velocity is going to be 0, because then it's going to start to go the other way. Our acceleration we've just found here, but because we're going that way, it's going to be minus g over 5. Again, t is not involved, so we're going to be using v squared is equal to u squared plus 2as. So 0 is equal to 1.4 squared plus 2 times minus g over 5 times s. And then if you just rearrange that, you're going to get that s is equal to a half, which is equal to 0.5 meters. So the total distance that it has travelled, if you think it's going to continue on for another half meter, it's already gone 0.7 already, so you're going to do 0.7 plus 0.5, which altogether is going to be 1.2 meters. Thank you so much for watching. I do hope the content of this video has been useful and helpful in your preparation for the mechanics part of the applied paper next week. Do like and subscribe, add any comments below the video, that would be greatly appreciated. Best of luck if you are sitting the exam next week. Check out the channel because there might be some more videos I'll put up, and there's the statistics help there as well. Okay, thanks everyone, see you on the next one.